Hey everybody, today I'm going to be talking about reliability testing. So first off, here's the agenda. There's quite a bit of things to go through today, so we'll start with definitions, and then the next several topics are kind of related to just reliability testing in general. So we'll talk about the different types of tests, where they show up in design, how the reliability engineer is involved in those, how to set up tests, or some of the factors that go into thinking about the testing. And then we'll talk about some of the specific tests like the Production Reliability Acceptance Tests, or PRAT, Reliability Qualification Demonstration Style Testing. We'll talk about Binomial Acceptance Testing, Burn-in testing, and sequential testing. And then there's a couple of reference documents that I'll show you. And that'll conclude this lecture. Now, the next lecture will have some more stuff on HALT, HAS, HASA, some of the other accelerated style testing. So today we're basically going to cover reliability testing as an overview, get into a couple of the tests, and then we'll continue with more tests in the future, next week. Some of the learning objectives are mentioned here. So we kind of want you to understand some of the roles of the reliability engineer. You know, the reliability engineer doesn't do all of the testing. They're one element of getting the entire system tested. So it's important to kind of understand that role. And that'll vary, of course, depending on the organization you're part of. But just kind of as a general rule of thumb, we'll go over some of the roles of the reliability engineer. I want, obviously, you to understand the different types of tests, the different types of reliability tests. And then specifically some of the information about those tests, which is kind of the last couple of bullet points. Okay, so we'll start off with a couple of definitions. And, you know, so for some of you that are a little bit more knowledgeable on reliability testing, you know, you'll have seen a lot of these terms before, and it's so they won't be anything new to you, but for some of you, these will be the first time you've seen these. So I'll go ahead and just run through each one real quickly. So ALT, or ALT, is accelerated life testing. This is tests where stresses are in excess of what the system actually sees during its normal life. So this is a way to test the life of the system in a shorter amount of time, right? Because of course, if the life of the system is 20 years, we can't do a 20-year test. We have to find some way to accelerate that. That's what accelerated life testing is. And it's kind of an umbrella term for some of the other ones we'll see in here. Environmental stress screening. This uses the word screening specifically because it's for actually screening out units that have issues. So it involves subjecting the system to stress, which then causes defects in the system to be found and essentially screened out. So we're taking a population, sending them through this environmental stress screen and through this screen and weeding out some of those. HALT is highly accelerated life test. So it adds on the highly to the ALT, which is the first definition. And so HALT includes various step stresses, and we'll talk about the stresses later. And those are conditions that overstress the unit under certain conditions and essentially, again, pull out the faults in the system or the failures in the system. Highly accelerated stress audit, or HASA. So this is similar to HAS, which we'll see in just a second. But instead of HAS, where it's screening 100% of the units, HASA is the same thing. It's just screening only a portion of the unit. So this is something that's applied after HAS has been applied. Okay. HAS is highly accelerated stress screen. So again, it's a screen, and it's put in place. And this goes after HALT has been applied. So we would apply them in the order of HALT, then HAS, then HASA. Okay. And again, it's an accelerated test. It's used to stress the system and essentially find those failures in the system and weed those systems out that are failing. PRAT is Production Reliability Acceptance Test, and these are tests used to assure the continued reliability of production hardware, and we'll get into that one a little bit today. RDGT is Reliability Development or Growth Testing, and this test is used to improve the system's reliability by identifying, analyzing, and eliminating errors related to production. So you'll notice I'm using a couple of different terms here, and they're really just because I've pulled definitions from various locations, but errors, defects, faults, failures, these are all, I mean the same thing. And it's related to the fact that some of these are more commonly used in the quality world, and quality likes to use terms like errors and defects, where reliability engineers like to use failures and faults. But I'm using these interchangeably at this point. They don't have any difference relative to these definitions. And then finally, RQT is Reliability Qualification Demonstration Test. And this is a test that verifies the equipment meets the specified reliability requirements. Okay, so to kind of get into the testing, we'll start off with why should we test, right? Why should we assess, test, demonstrate any of these different styles of reliability testing? And there's, of course, a lot of different reasons. Some of them are listed here. So to meet requirements, right, the systems engineering process dictates that we develop requirements. The requirements are essentially what govern the system. They're what shape how the system comes out, right? And so the testing, once we go through the process to develop the requirements, then we come up with a design. We assess that design analytically, so on paper, and then later, as we build the design, then we test it. And the analytical portion is also to verify the requirements, but the testing does the same, right? It's the next level of verifying the requirements, right? So that's one key thing. Quantifying the system characteristics, and I would say that's kind of synonymous with the second bullet point, understand the system better. As we test, of course, we'll have requirements that we're looking to meet, and that's essentially the main reason that we test. But as we test, we learn more about the system. We understand how it works a little bit better, and that certainly is a reason for testing as well. And that sort of information, if we're in the design process and we're trying to verify the design, then that sort of information then should be recorded as the system's being tested. That information is recorded and is then later used for things like FRACIS, failure review board type of information, or for subsequent designs, right? So understanding the system is certainly important. Understanding the system's limits, right? So we of course have requirements which dictate the limits, but if the system doesn't meet those requirements, we understand that. So we understand the limits are short of the requirements, but sometimes the capability of the limits of the system are far beyond the requirements. And it can be really valuable to understand how far beyond. So one thing we can do with testing is understand what those true limits are. For example, what is the actual life of the system? We may say that it has a 20-year life, but we may test and find that it actually has a 30-year life. And that can be really important as well. And so overall, if we're testing the system, one of the things that we're doing is really verifying the design process, making sure that as we went through the design process, we did it appropriately. So this slide here talks about the different types of tests, and there are more than I've shown here. And in fact, the next slide is going to show kind of a slightly different version of this. But these are some of your primary types of tests. We'll talk about the PRAT, RQT, and sequential tests today. But accelerated life tests, kind of an umbrella term for things like HALT and HASS. Environmental stress screening, burn-in, highly accelerated stress audits, and highly accelerated stress screening. There's all sorts of different tests. Also, the reliability development and growth testing is also known as TAFT, or Test, Analyze, Fix, Test, which we'll also cover. So there are many different types of tests. all with different purposes, also applied at different points in the design process, or throughout the life cycle, not necessarily just design, which is essentially what this slide here is showing. So we essentially have, if we kind of break out the life cycle into some really broad categories, we can say that there's design, production or manufacturing, and operation. And so we would apply things like HALT, RDGT or TAFT, sequential testing, and RQT in design. Right, so these are understanding the limits, verifying requirements, things like that. In the production manufacturing phase, we'll do things like Pratt, Burnett, ESS, HAS, HASA, and these are primarily focused on eliminating defects or failures in the design, whether they're designed in, or in more cases, whether they're inserted as a result of the production process. So like a solder defect, right? So a lot of these are going to be focused on finding those sort of issues that aren't, they in some cases could be designed in, but the primary focus of the production, manufacturing, screening, and test is to eliminate defects that were put into the system as a result of building the system up. So they're not designed in general. They're usually added in when the system's built. And so, as you can imagine, those types of reliability hits would not be part of the previous analyses that were developed for the system, right? Because we don't typically predict reliability based on manufacturing defects. We do it based on designed-in failures. And then the operational phase, there's not usually a whole lot of testing that occurs during this phase, and you can imagine once you've designed the system and you've produced the system, that's when it gets delivered to the customer, and essentially the testing is done. The only common exception to that, I should say, well, there's two. One is if there's a certification process for the system, meaning that it occasionally comes back in and is essentially recertified. And that sort of recertification is going to be using more of the production manufacturing style test. And so I've seen in the past at Raytheon where we've done for some of our systems 4-year certification. So every 4 years, the weapon system would come back to our facility and we would essentially recertify it using our production style testing. They weren't exactly production tests, but they were very similar. So that's one scenario that you'd find during operation where you'd be doing the testing. The other one is more of a physics of failure style testing, and that's a result of actually seeing a failure in the field. And the failure can be for any number of reasons, but sometimes there will be a failure. That individual system will come back to the facility to go through the fracas process, and if it's determined that there is a failure that needs to be better understood, a lot of times it'll go through a physics of failure style test. It'll get tested, and then analytically we can determine how that test is set up based on some physics of failure type of calculations, which is essentially accelerated life testing. But predominantly your testing is going to be either in design or in production and manufacturing. Okay, so the reliability engineering involvement for reliability testing. First off, the slide here says that reliability engineer is the focal point of reliability testing activities. That's true, but it's good to keep in mind kind of what the perspective is on that. So in terms of the intent of the test, that is true. In terms of determining some of the limits of the test, that's true. But that's not true from the standpoint of actually physically setting up the test. Predominantly in the DoD world, and if you're working for a DoD contractor or directly for the government, there's usually test engineers that are going to be part of reliability testing activities. And I think it'd be pretty easy to argue that the test engineer is kind of the focal point because they're the one actually setting up the test. They're the one actually conducting the test and recording the data. And so I just want to provide some context to this first bullet point. The reliability engineer is responsible for the intent of the test. They're responsible then also for taking the data once it's recorded from the actual test and essentially making use of it. And so the whole purpose of the test is kind of under the reliability engineer, but actually conducting the test is very uncommon for a reliability engineer to actually be part of that aspect of it. So just wanted to provide some context on that. And there's also a note here on the producer and consumer risk. And so in some reliability testing, determining the limits of the reliability test have to do with producer risk and consumer risk. And what I've found in the past is that those values, which are denoted with alpha and beta, they're usually organizational level. So we kind of had standard values at Raytheon that we'd use, and that's usually going to be the same. So those are usually organizational level, and if they don't exist, determining the producer and the consumer risk is something that would involve talking to the customer, being the consumer, and then talking to usually management to understand what the producer's risk is, because that will actually change that can change the course of the test, and those can be kind of important numbers. So it's kind of the reliability engineer's responsibility to go acquire those numbers, but to actually do so, it involves some outside stakeholders. The reliability engineer can be the test lead. And again, this just really depends on the organization and kind of how things are set up. From my personal experience, I've never been a test lead because if I got in front of a piece of test equipment, I wouldn't really know what to do. That's why we have test engineers, because they know how to hook everything up. They know about the system, but they also know about the test equipment. It's good to keep in mind that test equipment, I've always thought that the sum of the complexity of the test equipment for a system far exceeds the complexity of the system, right? So you take like a weapon system, for example, and you can kind of understand about how complex it is. The test equipment that weapon system has to see across its life cycle is far more complex than the system itself. And so the test engineer is a critical person in terms of testing the system. But one of the pieces, the valuable pieces that a reliability engineer can bring in that I haven't mentioned yet, and this also can involve the safety engineer, is there are certain energetics in the system and certain failure modes in the system which, if the system's tested incorrectly, could cause the system, one, to be unsafe. So if you think about a weapon system again, for example, if you light off a battery, that would be a very unsafe situation. Then you risk lighting off a booster, potentially lighting off a warhead, or lighting off other energetics of some sort. And so, or potentially just lighting off an energetic directly through a test. So the reliability engineer and then the safety engineer can be really important for understanding some of the things to be aware of during the test. And that's kind of where they can come in as a valuable test lead. And then the other thing that the reliability engineer would be involved with, kind of a high level, is determining the scoring for the failure. And one way to think about this is what really constitutes a failure. It's interesting because I've seen in practice that this is very poorly understood. We go into a test and it seems very obvious to think about what a failure means. And so, it's usually, okay, a dead unit is certainly a failure. But if you don't think about the exact test being run and kind of what some of the different outcomes might be, it may be uncertain what a failure is. And if you don't understand exactly what you're looking for, and specifically what you're not looking for, then often failures can cause, especially in DoD organizations, failures can cause a stop of a test. And usually when a stop test occurs, there's a whole big process to go through FRACIS and the failure review board before that test can be reconducted. And it hinges on the fact that if you don't understand what constitutes a failure, then inevitably you're in a situation where you have to stop the test, you have to go through the FRACIS process, and if you have to go through the FRACIS process, you have to wait to test and you have to wait to get your results. And so by thinking through in a particular test what constitutes a failure and what's meaningful to that test, you can actually avoid you usually still have to do a FRACIS process, but it won't hold up your test, because you can say before you start the test that if these things occur, then we're going to do a FRACIS process, but they're not related to this particular test, so we're going to continue. And usually that's a very acceptable thing. So the point here is that before you start a test, you really kind of want to understand what constitutes a failure and also kind of what does not constitute a failure. This slide here talks about what I'm calling the reliability affecting test factors. I didn't use the word stress here. You could use the word stress here, but some of these things are kind of fuzzy on whether I would call them a stress or not. But essentially, so temperature, vibration, mechanical shock are certainly stressors. These are very common stressors. They're the most common ones. And then also humidity. So I would say the first four that are highlighted in bold are kind of the most predominant and most well-known, most thought of types of reliability affecting test factors. And this is, I'm going to say this in this case is actually based on what I've seen in the past. This may vary a bit system to system. So if you're not talking about weapon systems, if you're talking about some of the subsystems within a submarine, then it's possible that those four primary factors are a little bit different. I think in almost all cases, temperature, vibration, and mechanical shock are going to be the primary ones. But there may be some other ones that, in addition to humidity, that play an important role. But the list shown here is a pretty comprehensive list. This is gathered from a variety of different sources, and these are just all factors that affect reliability. Anything that can affect reliability. So we have altitude, we have radiation, electromagnetic effects, electrostatic discharge, dirt and dust, voltage, power, noise, all sorts of different stuff. And salt spray is another kind of common one. There's actually a specific test for that. So these are some factors that when you're setting up a test, you're going to want to be thinking about. And certainly, and we'll talk about this more in future weeks, things like mechanical shock and vibration and temperature, these are actually some of the variables in which are the primary factors in a test. So for example, you have a test that goes through thermal cycles. It will determine the duration of those cycles, the limits of those cycles. But you may look at this list and say, well, what sort of environment are we testing in? Is there a potential for some sort of contaminants in the environment, right? If we don't control those contaminants, then we're allowing them to affect our test unknowingly, right? If we're just in for example, if we're just in an engineering lab where it's not a clean environment, and maybe we should be in a clean environment is really the question you might want to ask yourself, because in an engineering environment, in an engineering lab, there may be contaminants that could affect the test, and it depends on what you're testing. So, and same thing with radiation. If you're testing programmable logic devices, they're susceptible to radiation. And if you don't think about that prior to the test, then you may have radiation affecting your test without even knowing. And so it's important to look at this list when you're developing a test and kind of understanding what the different variables are that could affect your test and whether you're controlling those during the test. And controlling them could be just eliminating them to make sure that they don't affect your results, or specifically understanding what their value is, right? And that's easier for temperature than it would be for contaminants. So there may be some research that needs to be done before the test is actually run. So let's talk just a second about the value of testing. We kind of sort of hit on this a little bit earlier, but there's probably a little bit more to add to it. So one of the values of testing is understanding the reliability throughout the system's lifetime, and just kind of understanding throughout the test. Some of the tests can give you an idea of some more granularity on when the system is failing. So for example, how long is the infant mortality region of the test, right? And specifically verifying the MTBF, or the failure rate during the constant failure rate region, or just even verifying, is that center region, the bathtub curve for your system, is it truly constant, or is it actually slightly decreasing or slightly increasing over time? So testing can provide some of that sort of knowledge. It also can kind of help understand the accuracy of the predictions a little bit better. One of the major limitations about reliability predictions is that they typically focus on component failures as opposed to the connectivity of the system, right? So we can take two very reliable components and we can hook them up, connect them in a very unreliable way, and it turns out that the result of that is a very unreliable system, right? Our predictions wouldn't capture that. Our testing would. So it can help to kind of understand, from that standpoint. And then we can kind of think about testing across the life cycle of the system, and we can ask things like, how is reliability knowledge, just kind of generically, the knowledge we know about the reliability, the value of the reliability, the failure modes, how the system acts in different environments, so on and so forth. How is that knowledge during, conceptual design? Is it high or is it low? I would say it's probably pretty low, right? Unless we've developed very similar systems and they're legacy systems. In general, that knowledge can be pretty low, right? What about during PDR and during CDR, right? Or during LRIP, the low rate initial production, or during full rate production, right? As the system progresses. So the point here is that as the system progresses over time, we do more and more testing. Our understanding, our reliability knowledge, I'm using this term kind of generically, our reliability knowledge increases over time. And that right there is the value of the testing. We understand more about the reliability of the system over time as we do more of the testing, right? And as the system begins to mature. Okay, so now we're going to talk a little bit about test design and just some of the factors that play into test design. And I'm not talking about any particular reliability test at this point, just talking generically about test design. So the first thing is, in every case, a test has to have an objective, right? And there's a whole slew of different objectives that we can use for reliability testing. Some examples include reliability demonstration, so understanding the value of the reliability. Reliability improvement, so it could be understanding the failures in the system, right? Testing the limits of the system, understanding where those are, and then as a result of that knowledge, we can then go back and improve the system. We can make changes to the design to actually improve it. Reliability screening or screening, and as I kind of mentioned earlier, this would be getting rid of defects that occur during the manufacturing process. All right, so those are some examples of some objectives. The type of test, we can have sequential tests, which we'll cover a little bit later. We can have something like an accelerated test, right? Where we're actually testing the system for a relatively short amount of time, but that's representing, for example, the lifetime of the system, or actually sometimes the multiple lifetimes of the system, right? So there's different types of tests there. A very important one is the amplitude and intensity, duration, and timing of the reliability affecting test factors. So we went over the reliability affecting test factors. I have some examples here: temperature limits, vibration limits, humidity levels, right? So in terms of test design, we have to understand what are the values of those, and so I'm calling those amplitudes and intensities, right? So what are the actual temperature limits, high and low, not just high. What are the vibration limits, things like that. When do those occur, right? Are we doing, thermal cycling is pretty common to do kind of a sine wave. So we go from, we'll call it like a room temperature, and we might go to a high temperature first, and then go down past room temperature to a cold soak, to a low temperature, and then back up to a warm temperature, back down to a cold temperature. So we'll cycle, and then sometimes it's a sine wave, sometimes it looks more like a step function because we soak at cold and soak at hot for a certain amount of time. It just depends on the test. But understanding those values, when they occur, and how long they occur for. And so the when they occur is also important because sometimes we will have random vibration or shocks occur at a very particular time. And for example, we may have random vibrations during hot. We may have, and then those random vibrations may stop, and then we may do random vibration on the ramp down, and then random vibration during cold soak, and then random vibration during the increase. But it may not be random vibration during the entire time. And there may be reasons for that, because it may be that you're applying that to certain units, but not all of them. But again, it's important to understand amplitude, intensity, duration, and the time when those occur for all the different reliability affecting test factors. The variables that are being measured, and this goes back to something I'll mention again on the next slide, but understanding what constitutes a failure, right? If for example, the angle of the output of something, or the voltage output, or some other output is important, then that's a variable that needs to be measured. And most likely, that's a variable that is important in terms of what constitutes a failure. Right, so anything that constitutes a failure should be getting measured. And it's also important to understand not just the variables being measured, but how they're going to be measured, right? So, and this is important for sampling rate. So when testing a sample, when testing a unit, how you're going to measure the outputs. Outputs can be continuous. For example, a voltage output is very simple to get continuous. But measuring the angle is something that may be something that you get continuously, or you may be testing that every 5 minutes, as an example. It's very common during burn-in style testing where there's temperature cycling and random vibration to cycle the units and power them up just during certain times. And so you may, during cold soak, you may power the units up, test them, make sure that all the variables are correct, and then turn them off again. And then during the ramp up, where they're heating up, you may turn them on again and sample them again. And then during the hot soak, you may do that again. And if one fails during the hot soak, the limitation is that you don't know at what temperature it failed. You know that at hot it's failed, but you don't know the exact temperature it failed at, because you may have tested it at hot soak, maybe 120 degrees Celsius. You may have last tested it at 55 Celsius. So all you know is that it failed between 55 and 120. So you have to ask yourself before you start the test, do I need more granularity than that? Do I need to know every 10 degrees Celsius that the unit's working? Potentially you do. And it's interesting because that'll actually affect your test. It'll affect your ramp rate, how quickly you can warm up the temperature chamber, because it'll take time to turn on the units and test each one individually. If it's done automatically, which it most likely will be, you can probably do it fairly quickly, but it may take 5 minutes, and so your ramp rate of your temperature will be limited by that ability. So also important to kind of understand. This kind of goes without saying, but it's very important to understand the cost of the test, right? This is, ironically, one of the biggest factors in testing. It seems to always be an issue, always be something that is kind of being fought over, so to speak, and that is that testing is expensive. And the value that you get out of testing kind of has to outweigh the cost of it, right? But not only that, you have to understand your costs with some decent granularity, right? If your cost has a lot of uncertainty on it, the way that programs will typically look at it is what's the highest potential cost, and they'll use that as the cost value. And so not only understand your cost, but understand your cost pretty well. And you'll notice later in this lecture that that can be an issue, because if we're doing sequential testing and the amount of test time is uncertain, then the cost is also uncertain. And so it becomes kind of a highly variable. And so it's kind of an issue. Another factor in testing design is the number of units to be tested, which certainly plays into the cost of the test as well. But the number of units can be important for other reasons as well. One, your test chamber has to accommodate the units, right? And often the test chambers are obviously a limited size and can only fit so many test units. And so right there, you're limiting the number of units that you can test. The cost of each unit can be another way to kind of limit those tests. And also just kind of the ability to be able to turn them on during a test. You have to work that into your test chamber. That can also take up some room. The number of units that your program has available, right? And so coming from the missile or weapon systems world, we often only had a handful of units during design that were constantly kind of being messed with and tested in different ways. And as a result, if we were doing design testing, I couldn't test 20 units or 10 units. I only had one, maybe two or three to actually be able to test. So the number of units was always kind of naturally limited. Now that's a little bit different during production. Obviously, the production you can do up to the number of produced units, and so there's a lot more opportunity in production. But during design, it's kind of naturally limited. Duration of the test is another one. I kind of mentioned this was sequential testing, so the duration of the test can be open-ended or it can be fixed. A lot of testing is fixed, so there's a certain duration just specified within the test, and that's a major factor in test design, both in cost and what you're trying to determine. But it's certainly a factor. And then again, I'll say this because this is such an important point. Understanding that what constitutes a failure is such an important thing and something that really, really requires thought before the test occurs. And this is something that you guys can all immediately go back to your organizations, and the next time a test is run, just ask, what exactly are we calling a failure in this test? And what you'll find is there's usually a really obvious answer. If it's a voltage test, if there's no voltage, that's a failure, right? Obviously. But there's going to be a lot of things that surround that are much more uncertain. And so it's important to just kind of talk through that, have a discussion about it, and kind of bring up some what-if scenarios, and kind of understand those and build those into the test strategy. So if you're testing voltage, and let's say your built-in test tests voltage, and let's say your bit tests 100 things, one of which is voltage, which is what you care about, and bit fails because bit 51, which tests angle, as an example, fails. Is that a failed test? If you're testing for voltage, I would say no. It's important, but it's not a test failure. But unless you say that we're going to use bit, and the only output we care about is bit 100, which is the voltage, then there's an easy argument to say that if bit fails, the test has failed, and it has to go through an FRB process before you can go back and retest it. So just a simple example of there's a little bit more baggage that comes along with your test, because bit tests a lot of things, and unless you really think about it, you're going to end up in a scenario where you can't continue your test to get your results until you go through a month-long fracas or FRB process. Okay, so now it's time for a couple of quick examples. So I'm just going to I'm going to do this, give you this example, and then I'm going to wait for just a second. And what I want you to do is actually pause the video, the recording, and actually work this example out. And then I'm going to quickly go to the next slide. So the objective of this example, we'll say that we're going to test, and the objective is to determine the mean time to failure of a part. Okay, so we're going to test 20 units for 50 hours, so it's a fixed time test. And the values noted here, which are in hours, are the times at which units failed. Okay, so one of the units, for example, was tested for 10.8 hours, and at 10.8 hours, it failed. And then the balance of the 20 units, which is 12-ish or whatever, successfully completed the 50 hours. So 8 out of 20 failed prematurely with these values, and the rest went for the full time. And so the question is, what is the MTBF? And don't overthink this one. It's meant to be fairly simple. So go ahead and pause it. I'm going to go ahead and move on to the next slide and show the solution. Okay, so again, 20 were tested for a total time of, in each individual unit was 50 hours or the time it failed. Okay, so the way to determine the total amount of test time is essentially just to add them all up, right? So we add all the units that failed prematurely, we add up their individual test times, and then for the remaining 12, which is, you'll see is the 20 minus 8, those completed 50 hours. So we can determine that there was 824 hours of test time, and as a result, we can use a simple MTTF calculation, which is, oops, sorry, one second here. Okay, I apologize. I realized that there's actually an error in this calculation. The error, so the MTTF calculation is the total test time divided by the total number of failures. The reason is it's 103 hours. The reason there was 6 before is the previous example that I pulled this from was making the assumption that actually 2 of the failures that were recorded, in other words, these test times, were not actually considered to be failures. And that goes back to the whole what constitutes a failure, right? So that whole topic. And I had meant to update this to be that those were in fact failures, because if they're not, you're supposed to actually update the times up here instead of being a failure time, like 12.6, for example. If that were one that was determined to not be a failure, it actually should have continued to be tested up to 50 hours. And so, anyway, the example was changed. The way to do this is to take the total test time divided by the total number of failures, and that represents the mean time to failure. Okay, kind of a similar example. So one more example. In this case, 10 units were placed on test with a failed unit immediately replaced. In the previous example, when a unit failed, it was pulled off, so the test time was from 0 to when it failed. In this case, all units are replaced, and there are a total number of 8 failures. And so the question is, in this case, what is the MTTF? Again, pause the video for a second. I'm going to go ahead and keep going to the next slide. It actually turns out that this one's quite simple, because all we're really looking for is understanding how many units are being tested. That's 10. How many hours are each unit being tested for? And if you think about replacement, it doesn't really matter when the failure occurs. If it fails at 5 hours and we replace it, then it goes up to the full 20 hours. The 2 units together get the 20 hours. All we really need to know is the number of units, the total test time, the test block, right, which is 20 hours, and then the total number of failures that occur. And with that, we can use the same calculation. total test time divided by total failures. And as you can see, the MTTF in this particular example is 25 hours. Okay, in just a second, we're going to jump into some of the more specific types of reliability testing. Before that, I'll mention a couple of things. In terms of pre-test activities, these are just some things to think about, some things to remember. The first bullet point here is some stuff that you might need as the reliability engineer to make use out of the test results or to prepare for the test. So for example, the reliability prediction, because you might need to know what the reliability is of the system that was predicted, so kind of the desired one, or potentially even from a requirement standpoint, what the required reliability is, or the MTBF or failure rate. The design and performance test results, thermal and vibration surveys, and burn-in and debugging type of data. So some of this stuff can play a role in using the results of the test or preparing for the test. Defining failure scoring definitions. Again, this kind of relates back to what really constitutes a failure, but it's a little bit broader as well. And so the first point is what's relevant, what's not relevant. So that's an important for understanding the failure. The second bullet point is a little bit more kind of DoD world lingo. What's chargeable in terms of activities? What can you actually charge? What can you not charge? I threw that bullet point in. That's more of an organizational thing. Obviously, we don't really need to go into that much in this class, but there are some activities that are not chargeable in terms of reliability testing, whereas most are. And then the failure scoring rules should be discussed and negotiated with the customer and should be documented in your test plan prior to the test occurring, right? This is an important point, right? Because you want to bring your customer along the journey with you as you're developing the system, and you want them to buy off on how you're doing your reliability testing and what constitutes a failure and how you're going to score the failures, right? So it's kind of an important point. Obviously, you're going to need your test apparatus or your test chambers before conducting a test. This is where your test engineer comes in. They're going to be able to provide those. And it says obtain the test chambers. Really, what in reality what it means is get your system to the location of the test chambers. And that's actually an important difference because not all test chambers are local. A lot of times there's a test facility at a particular place in the U.S. and the system has to be sent to those. So there's usually a lot of work involved in getting your system to that particular location. So kind of being aware of that's important. Also, the random selection of test equipment, I'm going to go into more detail on this in a little while, but you have to have representative examples. That's a super important aspect. So I'll mention more about that here in a little while. Okay, so we'll start with the first reliability test. And just an FYI before I get started on these, between this lecture and the following lecture, I'm going to cover some of these, generalized reliability tests, Pratt being an example. I'm going to cover some of them in a lot of detail, and I'm going to cover them in some of them in very little detail. And so it'll depend on which particular one. So first of all, Pratt is Production Reliability Acceptance Test. So you can already gather by the title that it's conducted during production or manufacturing. And so Pratt is a fixed length test performed on samples on a periodic or scheduled basis or 100% production hardware. Okay. If we use the word sample, that kind of generally refers to less than 100%. If we're doing 100%, we're using every one. It's not usually referred to as sampling anymore. If we're sampling, it's usually kind of referring to less than 100%. just so you kind of understand the lingo. And that's usually how quality engineers talk about it. Some other names that Pratt's known by, because actually I would say Pratt is not a terribly predominant name for this test. There's not a whole lot of literature out there on Pratt, so you can also look, or if you discuss this with individuals, you can look up things like fly to buy, failure rate test, or MTBF test. Now, if you look at MTBF test, you may also run across sequential testing, which is different. So just be aware of that. So production testing regularly assesses the design reliability during the full rate production. So this is, once you're kind of after this LRIP, low rate initial production type of production. So once you're really into reliability and you're wanting to continue to verify that the reliability is being demonstrated. And so this would be, as an example, from a practical standpoint, let's say you have a program, you're in full rate production, things are verified, things are kind of moving along, things are pretty standard, and out of nowhere, there's a failure that continues to occur, begins to occur, and continues at a pretty high failure rate. And I've seen this in the past. One particular example was with a part that had a delamination, and it was an electrical part. There's delamination on the part, and it occurred at a very high failure rate. It kind of came out of nowhere, and it severely impacted our reliability. Because we were able to screen them out, the actual operational reliability was fine, but it really impacted so I should say it did not actually technically affect the reliability, but it affected the number of units that we could put out the door, and it actually was a cause of a dull saw. So the electrical parts by the OEM were being cut, and the saw was old and dull, and it was essentially pulling out parts of the part instead of cutting through it cleanly. So kind of an interesting side story, but that's an example of something that that might affect the reliability if not caught during production, and so Pratt's kind of designed for things like that. So this is a little bit more formal here. So Pratt identifies things like production workmanship issues. Solder defects are a very common one there. Issues in the manufacturing process, quality control procedures, and things along those lines. So again, all manufacturing production related stuff. The Pratt test is conducted in combination with environmental stress screening, which we'll cover later. So those two kind of combine together, capture the early defects. Okay. So that was a pretty high-level, quick overview on Pratt. This one also is going to be fairly quick. So reliability qualification and demonstration test, also known as RQT, RDT, or RQDT, a couple of different acronyms that it's known by. And I've heard this referred to quite a bit as reliability demonstration testing. So it's kind of a common name for it. So this is a test. It mentions that this is conducted on behalf of the government, and that's for us who live in the DoD world. If you're not in the DoD world, obviously that's not really relevant. But it's using production-approved items, so ones that come off the production line, to verify essentially the reliability requirements, to essentially say that the units meet whatever the reliability requirements are. So this goes back directly to reliability requirements. Okay, so this one, we'll go into quite a bit more detail on the binomial acceptance testing. And I provided a little bit more detail on this because I've seen in practice that what I'm going to show in this section of the slides is actually used quite a bit in practice. And so I thought I would provide a little bit more detail on it. So binomial acceptance testing, essentially at the end of the day, there's a variety of different variables you can kind of pull out of this. So I'll get to that in just a second. One of the big factors is determining the sample size. For example, determining the sample size to demonstrate a certain reliability. Right, that's a pretty common way to look at it. So this slide here goes through a whole bunch of factors that essentially affect the sample size and choosing the sample size. I've got these all listed here. I'm actually not going to go through these in a lot of detail. Some of these, I'll go through them kind of quickly. So the test, the type and purpose of the test can be one. That doesn't have a strong correlation to the number of samples. It's something that needs to be understood to do the test, though. The test duration, sometimes that'll affect the samples, sometimes it won't. It really depends. In this particular case, the samples I'm going to show, it does not affect it. What your MTBF or MTTF is, or mean life, mean cycles, failure rate of the design. Again, it really depends on how you're looking at that. If you have a requirement of reliability, then it actually will affect it. So in most cases, it does. The confidence level is one that is important, and I'll get to that in a minute. The confidence level actually depends on the perceived risk. So we have the producer's risk and the consumer's risk. So the producer's risk is the probability of accepting an item, so basically verifying the reliability of an item, when in fact, in reality, the reliability is lower than what you expect. That's the consumer's risk. I got these backwards. They're easy to always get backwards. So that's consumer's risk. The producer's risk is it's the opposite. So it's rejecting an item. So rejecting an item that actually has a good reliability. So that means you're essentially you're saying the unit doesn't have a good reliability or has a lower than expected reliability, lower than the requirement, when in reality it does. So those are the alpha and beta, or producer and consumer risk. And again, I'm going to look these up each time I talk about them because I always get them mixed backwards. So anyway, the point of this major portion of the slide is there are a lot of different factors that play into really the binomial acceptance testing method, kind of specific to the sample size determination. How many samples do we have to test? So there's some assumptions that go along with sampling. So reliability testing, very often, and in this particular case with the binomial acceptance testing, involves sampling from a population, right? And in order to do that, we have to do it right? And so in order to have a valid test when you're taking samples from a population, there are a couple of things that have to be met. So I mentioned this one earlier, this first one here, which is that samples have to be representative of a population. This is a really important one, right? Because if you can imagine, if you're sampling from a population, the idea is that you're going to test the samples and you're going to infer about the population. So you're testing the samples and you're going to say something about the population. If those samples poorly represent the population, because there's no true way to test the population, or when I say true way, maybe it's just not feasible, right? In destructive testing, we certainly can't, right? In destructive testing, we ruin every test, every sample that we test, right? So in that case, we're saying things about the rest of the population, and we're ruining the samples we're using. And if the samples that we are testing do not appropriately match up with the population, then we're going to inappropriately make assumptions or infer things about that population. So for example, I've mentioned some terms down here: engineering unit, engineering rat or testing rat, and golden unit. So these are terms you may or may not be familiar with that are good to be really aware of when you're doing testing. So engineering units, from what I've seen, are units that typically get tested over and over. They're ones that throughout the design process specifically are tested, they're fixed, they're retested. And when I say tested, I mean tested on all sorts of different things. When your SMEs or your designers are working on the unit, when they're going through their design process, they're doing ad hoc type of wiring to test different things or to see if a certain configuration of the design works. So I will claim that in general, engineering units are not representative of the population. I mean, they're kind of a well, they get beat up a lot, and they're not the specific configuration of the design. They get changed in a lot of ways. They get worn out. They're not very representative. And that's really what I mean by engineering rat or testing rat. This is just a term that I've heard used quite a bit. They're essentially units that they're usually available for testing during design. They're kind of being built up. They might even, in some cases, be a prototype, but they just get beat up. And so, again, they may or may not be representative of the true population. And it just depends, again, on what you're testing. So it's just something to be very aware of. Now, a golden unit, by definition, is representative of the population. So a golden unit is a very pristine unit that's said to be working in all ways. It is the ideal unit. It's the one unit that if your customer walks in the door and says, I want you to run this test, you don't grab the engineering unit, you grab the golden unit and you show them everything on the golden unit. So the golden unit is supposed to be the perfect unit. It's supposed to work perfectly in every way. Of course, it doesn't always, but that's the idea of it. So in general, we would say golden units are very representative of the population. Okay. Now, the second bullet point is also really important, and it depends on whether it applies or not. But ideally, to have a valid test, you have randomly sampled samples from the population. And if you think about during design, when you're trying to infer about a population that does not yet exist, it's of course hard to randomly select from that population, right? You have to test what you have, right? And that's where the fuzziness comes in during the design process. You don't have a population to sample from. During production, you do. And so during production, the units that you test should be fully random, right? Should go to your production line and walk down the line and just pull one off and say this is a randomly selected sample. It shouldn't be based on the way it looks, shouldn't be based on its prior test results. It should just be based on walking down the test line essentially and pulling one off, right? So random samples are really important, and the point of that is that those samples are the best way to get a representative sample of the population because you're making no assumption about the sample when you're taking it. It's completely random. And then sample MTBFs should be normally distributed. That's true, I guess, as well, but a little less important here. Okay, so with the binomial acceptance testing, the way that I've seen this done is usually related to a reliability verification, meaning that you're trying to prove out the reliability, and it doesn't have to be the system's reliability or even the parts reliability. So I'm using the term reliability a little generically here. It can just be the probability of failure, right? So 1 minus reliability of a particular failure mode, right? So I mentioned this idea earlier of a supplier had a dull saw and it was causing delamination of one of our electrical components, right? So we could prove out the reliability of that particular failure using this method. So we call it, just generically, it's called reliability verification, right? So in this case, we have N units that are going to be tested, and we're going to be observing X number of failures. So we're we're specifying some variables here. So n tested units, and x denotes the number of observed failures by time t. And t can be, in this case, usually what I've seen is it's a specified variable. So we say, if we're going to do like an accelerated test, we would do quantification of, for a particular failure mode, what is a lifetime given some accelerated factors. So we can, let's say the unit sees diurnal cycles between, 10 degrees Celsius and 30 degrees Celsius, and it sees those for 20 years. We can speed that lifetime up and say, well, instead of going from 10 to 30, we're going to go from -50 to 120, and I'm making numbers up here. But as an example, then we can test for 7 hours instead of, 10 or 20 years, right? And so then we'll test then usually one or a couple of lifetimes, and so that's the variable t, right? And we're measuring a certain number of units during that time and how many failures occur. So R is the number of allowable failures that can occur, and this is based on kind of a backwards calculation to say, given the reliability and given the number of tests that we're going to sample, how many failures could we see? Okay, so we can determine that as well. At the end of the day, what we're really trying to do here with this reliability verification, another way to think about this, is the variable x, the number of allowable failures. If that is less than or equal to r, the allowable, then we say that we've essentially met the reliability, right? We've verified the reliability. So our r of t that we're testing is greater than or equal to r, which is our known requirement. And if x exceeds r, then that means r of t is less than r. That's one way to think about it. So essentially, to do this process that I'm going to show here in just a second, we're going to need to know r, we're going to need to know n, t, little r, the number of allowable failures, and the confidence level. T is typically known. It depends on the mission. And again, it can be accelerated, but it's typically, I would say in all cases, T is a known variable. So we know what T is. We may have to go through the process to accelerate that, but T is known. R can be determined in a variety of ways. Although it's usually known because it's part of a reliability allocation or it's part of the requirements. So again, it's usually, and I would say in all cases I've ever seen, it's known as well. The confidence level, this is the one that's a little bit more fuzzy. It depends a little bit. The confidence level usually is 90 to 95%. I've used 90 a lot and I've used 95 a lot. It's pretty darn rare that it's outside of that. And the confidence level is related to the producer's risk, which is 1 minus alpha. So again, this is the idea, alpha is this idea of the chance of rejecting a unit, so kind of throwing a unit away, given that it was a good unit. So that's part of the calculation here. And that alpha value is usually 5 to 10%, which puts the confidence level between 90 and 95%. And I would say the most common is probably 95%. So then the remaining variables are n, the number of samples, and r, the allowable failures. And so the question becomes, how can we determine those? So I've got a spreadsheet, and this spreadsheet called the Sample Size Estimator SSE Rev 6A is provided for you guys in Sakai under Resources under Module 2. And this is a sample size calculator. It's called Sample Size Calculator, although it's a little bit of a misleading title because you can actually use it to determine a couple of different things. And I'm going to walk through an example here in a second. And this calculator has been very much used and it's very tried and true. It's been used by several different experts and developed over a while, so it's a very good calculator and it's very reliable. So I'm going to go ahead and pull it up here. Okay, so what you see here is the calculator itself. It's an Excel spreadsheet. There's quite a bit going on here. You don't really need to worry about most of the stuff in here. There's some notes toward the bottom. The steps here, so there's 4 different steps to essentially do a calculation. But I'll kind of walk through this real quick. So let's say, for example, again, this is, so we're gonna assume a confidence level here of 0.9. Again, 0.9 to 0.95 is pretty common. In this case, our probability of failure is 0.01, which represents a reliability of 99%, right? So just note that it's a probability of failure, not the reliability. That's why the value is really small, okay? So what we might say is, given a confidence level of 0.9 and trying to prove a probability of failure of 0.01 or less, or a reliability of 0.99 or higher, assuming we have 0 test failures, how many samples do we need? Okay, and this is already done, right? So that's the value here. So we need, and you would round up in these cases, so essentially you need 230 test samples. 229 or 230, I guess you could also round down. Okay, now let's say instead of having 0 test failures, let's say, well, what if we have 1 test failure? Okay, the value of the number of tests needed, the number of samples, goes up to 387.5, right? And we can continue to do this over and over, right? We can just, can put different values in and continue to look at, given the confidence level, given the probability of failure, what the combinations of number of failures and number of allowable failures and the number of samples needed, okay? But we can also look at this a little differently. So let's say instead of calculating the number of samples, let's say we know the number of samples, and we instead want to say, how many failures could we allow? So let's switch the example up, and let's just say we've got 200 samples. That's a set number. And let's say we just need to prove at least a reliability of 0.9. Okay, so that relates to a probability of failure of 0.10. Okay. We can allow up to 14.1, so 14 failures to occur to achieve this, given the confidence level and given the number of samples we have. Or you could say, well, you know, if I want to use less, I'll put in 100 instead. I can allow up to 5.8, so essentially, you know, up to 6 failures. And then we can also, so we can do this for the reliability as well. So let's say we've got, again, 200 samples. We're going to allow maybe just 1 failure. Another way this is used, it essentially says you can prove up to a reliability of, you know, whatever 1 minus this is. So 0.9817, or what I think the value is over here. Yeah, so 0.9807. So that's another way that this calculator can be used. You can look at the number of samples, the number of allowable failures, or the reliability / probability of failure. Okay, so it's a pretty useful calculator, and I've got an example on here as well. So let's say we have 0 failures, we have 45 samples. I guess I'm saying this a little bit wrong. So assuming we have a confidence level of 0.9 and a probability of failure of 0.05, so we're looking at 95% reliability. What are the combinations of allowable failures in samples, right? So it's 0 and 45, 1 and 77, 2 and 105, so on and so forth, right? So you might say, we've got a reliability requirement of 0.95. We need to test that. What we're first going to do is grab 45 samples, and we're gonna hope that they're all successful. And if we test 45 and they're all successful, you're done. You've proven your 95% reliability at a 90% confidence level. You don't need to test anymore, right? But along that way, let's say sample 36 fails, then what you know is now you need to test up to 77, okay? But if you see a second failure at 70, now you know you need to go up to 105, right? And what you can probably already gather out of doing this is that, well, if in reality, if you were to do that, at some point you might realize, well, I actually really can't prove a reliability at 95%, right? And that's sort of where you get to the point where you say, well, okay, instead of trying to go for 95%, which we realize we're not going to hit, we're going to say, for example, we had 0 failures, or we'll say, well, really, probably should say 1 failure out of 36 samples. My probability of failure is 10.38%, which is 89.62. That's really the reliability value that I got. And you could actually graph that reliability as a function of samples and whether the sample is a pass or a fail. And what you'd see is your reliability with 1 sample would be, of course, very low. Reliability with 2 and 3 and 4, it would grow over time. And then when you hit sample 36 and there's a failure, your reliability would jump down. And it would grow, grow, grow. And when you hit another failure, it would go down. So you could kind of look at the reliability as a function of the number of samples being tested and whether they passed or failed. And depending on what your application is, you can make use out of that data however you see fit. This is just another example. So at this point, it's kind of belaboring the point a little bit. Given a confidence level of 90% and 0 allowable failures, how many successful tests need to be performed to prove a reliability of 99%? So again, probability of failure 0.01, confidence level 0.9, 0 for a maximum number of failures. Make sure to double click where the orange box is to make sure that it's calculating the right variable, and it'll calculate a 229. I think I showed that exact example a minute ago. And just a reminder, these steps in this box in here will walk you through how to use this calculator. This is the equation that's used in that calculator. Just for completeness, I kind of wanted to show it. So you can see there's the producer's risk, the alpha. You'll notice the right side of this equation, although it's not shown, is the confidence level. So 1 minus alpha is the confidence level. It's got the reliability, the reliability that's trying to be demonstrated, right? Again, that's usually like a requirement or something like that. Sample size, the number of samples being tested, and the number of failures, or you can think about that as the number of allowable failures, right? So again, going back to some of the slides, a couple slides back, where we're talking about the number of failures that occur versus the number of allowable failures, you can think about it doing the calculation to say we need to prove a reliability of 0.99. We've got 100 samples, so we can determine the number of allowable failures, right? And then you go do the actual test, and if you test 100 and it's less than the number of allowable failures, then you've proven that reliability. And that's essentially where these equations down here at the bottom come in. Okay, but again, this is the calculation that governs that calculator. Okay, so next I'll talk about burn-in testing. And this will be nice to see the graph in just a second here, but the goal of burn-in testing is to screen out failed items as a result, in order to do that, you'll increase the mean residual life of the population. So if you can imagine producing components continuously, right? And thinking about the bathtub curve, right? So the curve which graphs the failure rate of the system over its life cycle, where it decreases initially, so it's high, it decreases to lower, it's constant, and then at the end of the life, it increases for wear-out failures. And that initial portion of the failure rate region is called the infant mortality, right? So if you can imagine kind of the system's life cycle, if you're producing systems that have defects in them, and those are going out and they're failing in the field, or failing with your customer, or failing in use, then you're going to decrease the reliability of that system. So the goal of burn-in is to selectively remove those items that'll fail early, and as a result, increase the reliability of the system, or as it says here, increase the remaining life of the system, okay? So by eliminating those that fail early, we can increase the mean residual life, okay? Burn-in is applicable to that infant mortality portion of the bathtub curve. So when there's a decreasing failure rate, as I'm calling DFR here, right? So that's when it's applicable. I'm going to show just a second. I'm going to show a specification model to actually look at the number of hours needed to calculate the number of hours needed for a burn-in test relative to the life. What I am showing also here is a cost model, and I've got a cost model for this as well. Due to time, I'm not planning to cover that, but I would say that if any of you guys are interested in that cost model, so determine the cost of a burn-in test, I can provide that. And if enough of you guys are really interested in it, I can cover it in a subsequent lecture. But just due to time, I'm not covering it in this lecture, but it is something that I do kind of have, and so if you want it, let me know. This other one is referred to more as the specification model. So if you look at burn-in, well, really this is looking at kind of the bathtub curve and the occurrence of failures over time. Burn-in failures are this initial region, which is specified with the large T. And again, the goal of burn-in testing is to eliminate the systems that have these early failures, or to eliminate the failures, right? So you can eliminate the system depending on what kind of product you have, or you can find those, if it's a solder defect as a result, right? You can find those failures and you can just fix them. Doesn't necessarily mean you eliminate the system. It just depends. I mean, if you're producing electrical components and one has a failure, typically you'll just throw it out. But if you're talking about a circuit card, which is worth a lot of money, then you'll go fix the solder defect. So it just depends on what your system is. But essentially, this initial region shows a lot of failures, and burn-in testing is meant to get all those out. The equation on the top right in the green box is the equation that's used to determine the value of the large T, right? So it's the one that's given some variables. This equation will allow you to determine the value of T through some math, right? And that's the time of the duration of the burn-in test, assuming no acceleration. In that equation, theta is, you may notice, by the way, that essentially that's the Weibull equation. So this is related to Weibull. Theta is going to be the scale factor, has units of time, and beta is the shape parameter. And also notice that it's set equal to 0, right? So essentially you can set the first exponential, the first Weibull equation, equal to the second Weibull equation. Okay, so to show an example, I think the easiest way to explain this is just using an example. So reliability testing has shown that a ground power unit used to supply DC power to an aircraft has a Weibull distribution, and that's nice because, right, the Weibull can reduce down to the exponential. So I'm presenting the Weibull case knowing that it's kind of the more generalized case, right? So it has a Weibull distribution with a beta value of 0.5 and a theta value of 45,000 operating hours. Notice, first of all, that beta is unitless. Also, for decreasing failure rates, beta values can be between 0 and 1. So using burn-in testing, your beta value should never be greater than 1. So determine the burn-in period necessary to obtain the required reliability specification of 0.9. Okay, so I'm going to just jump into the calculation. So first off, if you look at the reliability at 1,000 hours, which is the life, reliability at 1,000 hours, given the information that we know, is 0.86. Okay, that's using the beta value of 0.5. That's using the theta of 45,000 hours, and it's using a t value of 1,000. So essentially, if you do e to the negative 1,000 over 45,000 raised up to the 0.5, you get 0.86. Okay, so with our burn-in samples, if we don't do burn-in at 1,000 hours, we are not going to meet our specification. Right? The reliability is 0.86. We need it to be 0.9. Okay, so we need to eliminate some of those samples. And the question is, how long do we test for? How much life do we use out of the system to weed out some of those samples? And if we use the equation shown on this slide here, which is the same on the previous slide in the green box, we put in, again, 1,000 for T naught. We put in the 45,000 for theta, the 0.5 for beta, and also the requirement, the 0.90 for R naught. We just solved for big T, and I'm not going to show the steps for that, but the value comes out to be 126 hours. So by testing for 126 hours and eliminating those failures, we can get the reliability, the remaining reliability, to a value of 0.9. Okay, the last test I'm going to cover today is a sequential test plan. And this is something that you guys have probably seen a little bit before in SE4321 suitability. But essentially, sequential test plans or sequential tests are usually used for determining the MTBF, or the failure rate of the product. And one of the known, it could be an advantage or disadvantage, depending on how you look at it. One of the known aspects of a sequential test plan is that they can result in an early determination, early decision for accepting the MTBF. So typically we think about these with MTBF, and we can get to accepting the MTBF quite quickly, which is really nice. But the downside is that this is not a fixed length test. It's an open length test, as you could call it, which I don't know if that's an official term, but that's the way that I've kind of called them out. So with an open length test, they can really go for as long as the test allows, which means you're essentially getting to a certain criteria to stop the test. And if you don't get to that criteria, it can go on for a long time, is the point, and it can cost a lot of money. And so it's really important to know that. But if in a lot of cases, sequential test plans are valuable because they get to a decision very quickly. So the irony is that the variability there can be kind of scary, but in general, that's actually kind of the value of the test. So these are look at accepting or rejecting the MTBF. It assumes a constant failure rate. So the catch there is that this would be done post burn-in, right? So you're looking to determine the MTBF, or the failure rate, in the constant failure rate region of the bathtub curve. So you got to get you have to get past your infant mortality failure rates, and that's why post burn-in is the time that this would be applied. Okay, this is what a very typical sequential test plan looks like. On the left, or the vertical axis, the left side of this graph is the cumulative number of failures. On the horizontal axis is the amount of test time, and you may also see the horizontal axis, instead of being test hours, which is shown here, and unfortunately it's not labeled, but it's test hours. You may also see that as multiples of MTBF. So in this case, if the MTBF were 100 hours, you may see 1, 2, 3, so on and so forth. So just be aware of that, which it can be confusing, because if you think about those in hours, it'll look like it's a really short test when it's really not. So the idea here is that testing begins at the origin. So it begins down here, and as testing, so a certain number of units are placed on test. As the testing commences, it begins to move this way. Oops. And then as a failure occurs, that gets recorded in terms of jumping up to one failure, right? As testing continues, again, it jumps up when another failure occurs. And the goal, you can think about this almost as a game, the goal is either to hit this line here, which is the accept line, or to hit this line up here, which is the reject line, right? So as test time continues, a third failure occurs, it jumps up again, and then it continues, and once you hit this value, and there's some math involved in determining what this exact value is, because this is a linear line, right, and the value on the y-axis is 3, and so on and so forth. But once this line is hit, then the MTBF is accepted. Okay, that means that if your MTBF is 100 hours, and that's specified to begin with, then that value is accepted, and you say that that's the MTBF of the system, or whatever's being tested, right? So if this is system being tested, that's the MTBF of the system. If it's a subsystem or a part, it's the MTBF of whatever's being tested. And if you hit this line up here, the MTBF is actually rejected, okay? This shows a table out of Mill Handbook 781. So there's a couple of inputs that go into doing the math behind a sequential test plan to sort of set it up. You need to know alpha and beta, which again are the producer and consumer risk. So these typically take on values. From what I've seen, they're usually 5 to 10%. In the table I'm showing here, obviously they're between 10 and 30%. Seems like a slightly high value to me, but that depends on the industry you're in as well. So in weapon systems, that tends to be a little bit lower. And then theta naught and theta 1 are used to determine the discrimination ratio. Theta 1 is the lower test MTBF, so the kind of the lowest acceptable MTBF. Theta naught is the upper test MTBF, so that's the desired MTBF. And given that information, they determine what's called the discrimination ratio, which is just the theta naught over theta 1. And that discrimination ratio plays into some other calculations, and some of the result of those other calculations are determining the expected time to get to a decision. And this would be for planning purposes, right? If you're going to say, well, we have to pay somebody to do this test, we have to pay for the test equipment if we're doing it at somebody else's facility, we would like to know what the expected test time is, which is shown on the far right side, which is shown in the center column, or what's our worst case scenario? It's going to be about 49.5 hours, right? So just some good information to have. It's important to note the far right 3 columns are in multiples of theta 1. So as an example, if theta 1 is 100 hours, right? So your lower MTBF is 100 hours. It's important to know that your maximum time is 100 times 49.5, which is 4,950 hours. So it can be quite a long time. but again, that's also without anything being accelerated. Section 5.9.5 in Mail Handbook 781, which is also on Sakai under the Resources Module 2, gives a really nice step-by-step walkthrough of how to develop the sequential test plans and how to develop the limits on this and the values within this table. So that's something that I would highly recommend you guys go and look through. On that note, reference documents for today's lecture. The primary one is going to be Mail Handbook 781. This is one of the primary reliability testing documents for systems. You'll notice on Sakai, I have a bunch of other mill handbooks and mill standards. I basically pulled everything related to, in some way or some form or fashion related to reliability testing. And I've thrown all those up on Sakai, so you guys have all those resources. I think they're valuable to have. But I'll point out that Mill Handbook 781 is the most predominant one and really the kind of the primary one that you guys would want to be using kind of in general. So with that, that's the end of today's lecture, and I will be posting homework up fairly shortly. All right, thanks guys.